if you've ever gone, how many people have ever gone hiking in the woods? When you went hiking in the woods, did you get a map from the U.S. Geologic and Geodetic Survey? No. Well, you should, otherwise you'll end up like some of those people out west that have to call for help on their cell phones because they're out hiking around where they're not supposed to be. And they don't know how to get out of the problem they've created. So the way a survey map works is that, of course, there are undulations in the surface of the Earth, mountains and valleys and things like that. And basically what they do is they fly over it and they take a picture from different angles. And by taking a picture from different angles, they can figure out the different altitudes above sea level, different points on the Earth. And then they connect all the points that have exactly the same altitude above sea level, and they connect them with a line, and that's called a contour line. And in one of these maps, when the contour lines are very close to one another, it tells you that the hillside is very steep. When they're very far apart, it tells you that the hillside is very shallow. Another place where you see the same kind of idea applied is in the back page of USA Today, which has the weather map. Anybody? Yeah, it's nice. That nice colorful map on the back page of USA Today. It's got a map of the U.S. or maybe the world. I don't think I've ever looked at that page more than once or twice in my life, so I don't get exactly what's on it. But in the map of the U.S., they have so-called isotherm. So all the places that have the same temperature are colored red. All the places that are really cold that day are colored blue. So they got all kinds of shades of yellow and green. That works the same way. So if you laid the map on the floor and the vertical dimension was the temperature, all the places that are red have the same vertical height that corresponds to temperature. So when you're looking at a bivariate normal, say, it's nice. It looks like the Liberty Bell sitting on the floor. How many people have been down to Independence Hall to see the Liberty Bell? Either you went down on your own, or you dragged relatives down there when they came to visit. So you got to do this whole sightseeing deal. So you may have seen it 20 times because 20 different relatives come from different occasions. They all want to see the Liberty Bell. Pretty much everybody knows the whole time. If you were to look down on the Liberty Bell and plot all the points on the surface of the bell that were exactly the same height off the floor, you would get a perfect circle. And then you picked another height off the floor and you connected all those points and you get another perfect circle, different diameter than the first one. And then if you squashed all those perfect circles down onto the floor, you'd get a set of concentric rings. Well, imagine that you did the same thing with the normal probability density function. You took out you were looking down on it and you drew rings on it that were exactly the same density. And then you push them down onto the surface of the floor. You've got a two-dimensional representation of a three-dimensional figure. But that's in the case when the two normal random variables are independently and identically distributed. Suppose that they are identically distributed, but they're not independent of one another. When x is big, y is big. Well, what that does is it takes that Liberty Bell and it squishes it into an ellipse. And the principal axis of the ellipse has an angle, horizontal, and that angle tells you what the correlation is between x and y. The angle of the principal axis away from the horizontal tells you what the correlation between x and y is, but it's an ellipse. And so sometimes it behooves us to take that ellipse, tilt it back onto the axis, and then squish it to a circle. So that the covariance matrix of the new random variable that we're working with is just an identity matrix. It makes the algebra much easier if you can work that kind of transformation. It's always easier to manipulate an identity. But if you have a bivariate normal that's not an identity matrix, well, it's symmetric. It has numbers in all four places. And so bookkeeping is easier if you do the transformation and convert it to something that appears to be IID. And then at the end, when you're all done, whatever you're doing analytically, you can convert it back to the coordinate system you started with. That's why
nowadays, there are all kinds of the models that develop.
And that's pretty what you're asking.
I'm thinking about how using your models to specify covariance all kinds of things.
Yeah, well, we're going to come to that. But part of the parable of this story is that you've heard about that in regression analysis there are a bunch of pathological diseases that we worry about. And one of those pathological diseases that we worry about is heteroscedasticity. Heteroscedasticity tells us that in this garden variety model, the errors are no longer identically, they might still be independent, but they're not identically distributed. The variance of UI differs from the variance of UJ. We still want to know, one of the questions that we might ask ourselves is when the variances are not constant across the subscript I, is there an estimator that has better statistical properties than least squares? Another pathological and so it turns out that we want to transform the model of the matrix so that we can go from the matrix where the error covariance matrix is not scalar diagonal to one that is scalar diagonal. Makes our life very simple to derive a new estimator. Turns out that in doing that rescaling, we just rescale the whole model and poof, we'll get back to a world of garden variety regression. Another pathological disease that I was talked about was serial correlation. And you'll recall that in serial correlation, today's disturbance is in part determined by what happened yesterday, or maybe even the day before. In that case, the error covariance matrix is not only not scalar diagonal, it's not even diagonal. But fortunately for us, it turns out that it is a banded matrix. There's a diagonal term, there's diagonal where all the terms on the diagonal are constant, and then the next diagonal is constant, and the next one out further out is constant on that diagonal, but smaller, until we get all the way out to the extreme corners, where there's just a number which is smaller than any other entry, but there are bands along the diagonal. Well, we now know, as a result of your question, that we can take that error that joint density, which is no longer spherical, and with suitable transformations, we can make it spherical. Once we know how to make it spherical, we can derive an alternative estimator that has the same properties, the same great properties as least squares. When you took beginning statistics, you were using the sample mean to estimate the population mean. You wanted to use the sample mean to infer something about the population, right? And you used the sample variance to say something about the population variance. You wanted to infer something about the population variance. And so along the way, you stopped and you talked about the properties of those two estimators, x bar and s squared, right? You said things like the mean, the sample mean, is unbiased, right? And you also said things like, in the class of linear unbiased estimators, the sample mean is efficient. So efficiency is a statistical property of a random variable of an estimator. And you also talked about the fact that the sample mean was a consistent estimator of the population mean. Do you remember having those conversations at one time or another? You can nod your heads. Yes. At the smallest variance among the competition.